seminar series. My name is Gaiman Yi. I am with the California Institute for Energy and Environment. I'm also the Technical Director of I-4 Energy Center. And it's my pleasure to introduce our speaker today, Dr. Roland Winston from UC Merced. Dr. Winston is also the Professor of Natural Sciences, the Professor School of Natural Sciences and School of Engineering. He's also the Director of the UC Merced Energy Research Institute. Areas of research interest include solar power and renewable energy, elementary particle physics, and non-imaging optics. So let's give a good welcome to
Well, thank you very much for inviting me. Is this audible? Yep. And special pleasure to be here in this gorgeous building. I gave a seminar I think a couple of years ago in the older building, and I'm very impressed by your new headquarters. Also, last time last seminar, I had a really bad cold, so this time I'm less unfortunate, more fortunate. Okay, so I'll tell you a bit about what we're doing at both at UC Merced and also in the other campuses, because as mentioned, we have a new energy institute. It's not the one that was said. It's actually the California Advanced Solar Technologies Institute, and Berkeley is an important member of that, so I'll be talking a bit about that. Okay, so here we are on the map. We're close to Yosemite, and that's our location. And when we started building, we looked like that. You can see the Sierras in the background. And we actually had our first graduating class last May, and that graduation put us on the map because of our commencement speaker, okay? So now more people know where we are than they did before. Okay, so let me tell you a bit about this new institute, which is very exciting for us, because first of all, because of the members. You'll recognize your fellow colleagues from Berkeley, and we also have Santa Barbara and Merced. So, and I hope some of the Berkeley group is here. They told me they'd come. Can't rely on faculty. Oh, there's one of them. Eli's walking in the door. I just was saying, I hope that some of the Berkeley colleagues are here, and by golly, you're here. Thank you. So, we should clear out. So you can somebody take my space. Just take those plates away. Those should just go away. Is there a place I can throw? Is there a place we can put that? Just throw that away if you can. You can just throw my lunch away. I'll take the water. Thank you. All right, so I wanted to make sure that, Eli, you saw your name on the slide before I changed slides, okay? All right. You'll see it again. So what do we do? It's a 3-campus collaboration, and it was started by UCOP. In fact, the official start is January, and it's a 5-year program, which will hopefully have a longer life than that. And it's the only solar energy collaboration of this kind in the system. So we're very pleased with that. So we're going to be developing new solar energy technologies and also be important in technology transfer, which you'll see threads of. We're doing some of this already. You'll see threads of that as I go along. Okay. Right now, and this is going to change, but right now, the topics include nano things, solar cooling, daylighting, concentrated design, and the commercialization. We'll talk a bit about that. But this is going to change with time. That's sort of a snapshot of what's going on right now. Okay. All right. And of course, this is the sort of things we hope we will do, and what we will do is probably going to be a totally different list. Okay, so let me start with what I want to talk about. So I want to tell you a bit about the kind of optics that we do, and the best way I can introduce it is to show you a question posed to me. I was giving a seminar like this at the Raman Institute, okay, it's in Bangalore. And the gentleman who posed that question is Raman's son, so I paid attention to the question, okay? So he wanted to know, what does geometrical optics know about the second law of thermodynamics? So that's an interesting question to ask, okay? So let me kind of show you how there's a huge connect between those two subjects. This is not the optics that the students here learn in your classroom, okay? It's different, it's very different. So let me first show you how a very simple exercise in thermo gives you an immediate connection to optics and shows you there's something underlying going on, okay? So for example, let's consider the sun as a black body. We can measure its temperature without going there because we just measure the peak of the spectrum. It tells us the temperature, okay? And from that temperature, we know the surface solar flux, which is roughly 60 watts per square millimeter, roughly, okay? Now, when we get here to our planet, to the Earth, and we measure the flux above the atmosphere, which is now done very accurately with satellites and so on, it's about a little over a milliwatt per square millimeter, okay? Well, there's a ratio there, about 40,000. That ratio happens to be 1 over the sine squared of the angle of the sun subtends. Is that a coincidence? No. That's a deep thermodynamic statement, okay? So there's a connection between maximum concentration and the angular subtense. And the way you get that connection, at least one natural way, is to invoke thermodynamics, okay? So bear that in mind. There's another geometrical way of doing it. This is for the students, okay? I just invite you to consider how the flux from the sun falls off as 1 over r squared. You know these 1 over r squared laws are not restricted to E&M, okay, or gravity. They're whenever you have a conserved flux, you get a 1 over r squared law, okay? So if you look at that triangle, right triangle, and compare the flux on the sun surface and on the Earth surface, that's just sine squared theta, right? So that again tells you that should be the law of concentration, the maximum concentration. If you could do better, you could have a perpetual motion machine. Everyone knows that's not possible, okay? So that's another way to get at it. So I recommend this as a small exercise for anybody interested here. Okay. All right. So what I have to tell you about has a lot more to do with thermodynamics and essentially almost nothing to do with optics as you learn it in school. And I think that's still the case. Not just the way I learned in school. I think that's the way the students learn in school today. Okay. So let me give you a sense for how this is so. I'm going to step out of optics and I'm going to go into, of all things, furnace theory, the theory of furnaces, okay? Imagine that, theory of furnaces, okay? So I learned this stuff from a very great Chicago professor where I spent most of my professional and student life. Chandra, here's what Chandra looked like. And from his beautiful book on radiative transfer, I learned all this stuff as a student. Okay, so let me tell you a bit about the theory of furnaces. So imagine now, so you're going to switch gears. And what does furnace theory have to do with optics theory? Well, that should perhaps evoke some curiosity. Okay. So what I have here schematically is 4 walls. First 3 walls and then 4 walls. Let me get to a laser pointer. So I've purposely made them curved because it's a very general kind of thing. But let's start with 3. I can do 3 better. Now this is all due to an MIT professor, Hoyt Hoddle, and it's written up in a book on radiant heat transmission by McAdam. So if you want to follow this up. And let me show you how, simply thinking about how the walls in a furnace, you can think of this room, okay, as a prototype. So how much heat exchange goes from this wall to that wall, for example, okay? By thinking about that, we get to perhaps the deepest principle in optics, perhaps the deepest one, okay? All right. Let's start with 3, okay? So the challenge here is to figure out how much energy goes between walls without doing a single calculation, okay? Not a single non-trivial calculation. These are what I have to show you are absolutely trivial calculations, totally trivial. Okay. So I want to know, for example, how much energy gets exchanged between 2 walls. Well, you know, let's just first of all count up how many unknowns there are and how many things you know. There are clearly 6 unknowns, right? There's 6 ways you can take 2 out of 3, right? Okay. Are there 6 equations? Well, there's a set of 3 which simply tells you if the energy starts here, it's going to end up either here or here. That's energy conservation, okay? So that's these 3. Are there 3 other equations? Yes. The 3 other equations are that it is impossible for one wall in this room to cool off and the other one to heat up, okay? At equilibrium, we know that doesn't happen. So that's these 3 equations. So if 3 equations, more. Now we have 6 equations, 6 unknowns. You know there's a solution. Since the equations are so darn simple, you don't have to work them. You can do them by inspection, okay? I claim you can do them by inspection. For example, the transfer between 1 and 2, it's got to be symmetric in 1 and 2. It can't be symmetric in all 3. So it's got to be something like that, okay? So you could guess the answer without actually working out these really, really trivial equations. Notice that you've solved a problem which sounds hard, at least it sounds hard to me, without doing a single calculation, okay? Those are the best kind of answers in physics when you can get at them without doing a detailed calculation, okay? Now I sound like a professor. Okay, so anyway, let's go to 4. Let's go to 4. What I'm after is, say, exchange between 1 and 3, okay? Well, if you can do 3, the 4 just 2 3s, so I'm not going to bore you with doing that. But for the 4, you can almost guess the answer. Like say 1 to 4 is symmetric in these, symmetric in these. So anyhow, there's a word for this that engineers use, and that is this. If you want the radiation between, say, 1 and 4, you tie strings to the corners, and there are 4 ways you can tie strings. You can tie strings to the corners right across. Those are short strings. You can tie strings the long way. And the answer is, for the radiation transfer, the answer is you add up the long strings, you subtract the short strings, and that's the answer. Is there anybody here who has ever heard of this kind of stuff? Oh, boy. You have. Wonderful. Okay, the Hollow strings. Okay, they're gorgeous. People don't use them, I guess, because furnace theory is not at the top of everybody's list of things that they think are interesting. But it's darn interesting, it turns out. All right. So out of this, you can get yet another way to get concentration limits. If you just consider say you go from 2 to 3, okay? If you just consider the long string and the short string, the difference here, as everyone knows, was ever done you all do this when you do interference from a faraway source. As these edges go far away, these are parallel, and the difference is just this length at the side of the angle. So there you get the angle comes back, okay? And if you want sine squared, you rotate it. So Fresner's theory again gives you a limit to concentration. It connects the first and second law to optics in this way, okay? I think that's kind of neat. Okay, so what's even neater is that, okay, so you can say, oh, so what? So this is boring. But you can actually use these strings to design optical systems, and that's not boring. That's interesting, okay? You can design, and when you use these strings to design optical systems, you know they will obey thermodynamics. You know they will be thermodynamically efficient. You know there'll be nothing more efficient, okay? So what you do is you take these strings and you bring it into your optical system. And the best way to show something very often is just to do it, okay? This is showing by example, not showing by proof, not showing by argument, show by example, okay? So here's how you do an optical system, a very simple one, which collects radiation, satisfies this maximal sine squared theta condition, and uses strings, okay? So here's the absorbing surface. You can, if you want to be practical, this might be a solar cell, okay? Or anything, or it could be a light source. Okay. Now, to do the radiation part, you are instructed to, so we want to do an angle theta. You were instructed to take something which I noticed in my hotel room this morning, a shower curtain with a slider, okay? I had that this morning. And we're going to tie a string to the slider, and we're going to tie a string to this surface. And the slider is at angle theta, okay? So this is showing by demonstration, showing by doing, okay? So you take the shower curtain, you incline it at angle theta, you attach a string. String's going to be in red in this thing. So follow the string, okay? String starts here. Now this string is not going to change. It's the same darn string. But the slider will slide. That's what sliders are supposed to do. Okay, so the slider slides along, and in the end, I just made it symmetrical. It makes you an interesting looking figure, which, it turns out, takes radiation, not just at this angle, but all angles in between, and brings it from this aperture to this aperture, or if it's rotated, from this area to this area. And does it satisfy the sine law? It does, because if you simply look at the string when it starts and look when it ends, the part left over is just this sine angle, okay? So there you go. Done. Okay, done. Those are just fancy words for sine theta. It'll come. This fancy word will come back. That's a word people use in optics. You don't need to have heard it before. You don't need to remember it. Okay. So let's do it for a more interesting situation. Let's do it. So the second solution will come up in the solar work I'm going to describe to you. So in this case, your absorber, your target, or your light source, if you want to do it backwards, is a cylinder, okay? So now we have a cylinder. What do we do with the cylinder? If you remember our Hodel string thing, the walls were not straight. Well, the wall here is actually a cylinder. It's not straight. So you tie the string to the cylinder, and you unwrap it until it eventually goes over to the slider, okay? This is so trivial, right? You just keep going. Remember, there's no calculation of it being done here. Okay? You don't see any math. And when you finish, you've got your answer. And if you think about it just from before, the aperture here is just the 2 pi r or something. So it's the circumference, as it should be. It's the whole, because the string unwrapped from a cylinder, it's the whole circumference divided by the sine of the angle, just what you want. Okay. That's kind of what it looks like. Okay, there's another way of thinking about these things which is more abstract, and that is, if you like phase space, which some of us in this room do, Eli is still here, and you can think of an incompressible flow in phase space. That's that's very similar to, say, the flow of water, because water is pretty incompressible. If you think of it that way, you get kind of a similar kind of answer. So let's contrast what people do in imaging optics when they design cameras and lenses to what we're talking about here. So in imaging optics, let's just do it in one dimension to make it really simple, just one dimension, like this, just X. You're imaging points on a pencil, okay? Points on a pencil. So an image is a point-to-point map. An image is a tough thing to do. Lots of conditions. It's difficult. But if we think of phase space, the first thing we have to do is double the dimension. Not only do we have the position, we have to have its direction cosine. Okay? Turns out direction cosine is like the momentum. Okay? So now we have, instead of just one-dimensional things, we have a two-dimensional thing. And if you think about not having, so imaging has to map stripes to stripes. That's a tough thing to do. Map whole vertical stripe to stripe. The thermodynamics only requires you transport that energy. So let's just transport the surface. The green doesn't show up so green. Let's just transport the surface. Everything inside stays inside, and that's another way to get maximum energy transport. Okay. So just words. Okay. So that's just pretty much what I said. Just think. So the phase-space picture is the other way to get at this subject, and historically that's the way I got at it. I didn't know the thermodynamics so well. I wasn't comfortable with it. I'm not sure I still am, but I was comfortable with phase space. I was a good student of mechanics. Okay, so you can do all that. So this is a lesson for students that if you pay attention to a course in which you might consider a rather dull subject, it might give you ideas for something more exciting. Okay. Yeah, here's a little picture of what I'm talking about. Suppose you're doing the imaging thing. You need a large vehicle because you got to transport all the information. But if you're happy to just transport the energy, you can scramble things up, and a little Prius will do it. This is what this is intended to be. So I just heard a phone. It's not mine, but I want to make sure mine doesn't do the same thing. All right. So applications, okay, applications. We apply this at UC Merced to solar collectors which have thermodynamic properties of efficiency and don't have to track. So you get something back for that. Why do you have to track? Normally, people think you have to track because the solar, as you know, the solar inclination goes over about 30 degrees, 60 degrees total over the year. It's the way it is summer and winter, okay? So people thought you had to track. Why is that? Well, they thought you had to track because they were applying imaging techniques. And if you apply a parabolic trough, and I should say this, if you apply a parabola, and I'll come back to parabola at the end of my talk if I have time. If you apply a parabola, you find that your concentration is 1/pi sine 30. Okay, that's just sort of accidental. And since sine 30 is a half, this is less than 1. So you'd be dumb to do this, okay? But nature tells you it's 1/sine theta. Nature says 2. 2 is good. 2 is actually, we make use of 2 in our current work to get 200 degrees centigrade very handily, okay? Okay. Okay, so let me launch into a very practical application that we're involved with right now, okay? If you compare, so our job now is to create heat at 200 degrees centigrade. If you look at other non-tracking technology, they're called flat plate collectors, okay? Flat plate collectors die at 100 C. They don't boil water, okay? Well, we want something that holds up at 200, so we want this kind of thing. Okay. We're applying it to cooling. Why? It just seemed like a neat application of 200 C. There are cooling machines which work very well. This is turned to Fahrenheit, 400 F, okay, which work very, very well at 400 Fahrenheit. So how do you use heat to cool? Let me just say that these are well-known machines, and if you want to know about it afterwards, I'll tell you after the seminar. But you don't have to invent this. You buy these, okay? What you have to invent is the solar part if you don't want to track, because known solar collectors, by and large, either don't get this temperature or they track. So anyhow, that's a little project we're doing right now, mostly a student project, to turn 400 degrees Fahrenheit oil into 40 degree Fahrenheit water, okay? All right. So to start the project, we came to Merced and we had to build up an infrastructure. We built up a testing facility which sends hot oil through these pipes, and then we have to make various measurements. This being a technical audience, I'll show you how our flow meter is. It's a Coriolis force flow meter, so it's a fancy way of measuring flow rate. We actually use calorimetry. We actually don't do so much of that. And that's what our first collectors looked like, made by a furniture company and local furniture company. That's what they look like. They don't track, sit on a stand and do all that. Okay. Now for our demo, we didn't want a whole bunch of these. It's too cumbersome, and we wanted something that looks a little more practical, okay? That's just a close-up of that. So the next version, I should have shown this. So this is just to show the non-tracking. These angles, to convert to time, 15 degrees per hour. So 60 degrees is 4 hours. So plus or minus, so 8 hours, nice and flat. Actually picks up at the ends, which is nice. So you get a decent efficiency of about half. And if I can see that. And it's manifestly non-tracking, just flat, okay? Nothing moves. All right, so what do they look like? Conceptually, I'll show you some nice pictures of them. Nice receiver vacuum tubes. So there are details. I'm not giving you all the details because it would take longer. But the receivers are vacuum tubes to retain the heat. And these are the string collectors. And they look kind of like, still these are conceptual drawings. Let me just show you. I'll show you the real thing in just a minute. Still conceptual drawings. Real thing, okay, one of my students, and that's what they look like. Nice things out of plastic. That's a bank of 10, and there'll be 16 of these to run the cooling machine, okay? So you can kind of make them out here. Just a thin plastic. Of course, they'll have reflectors attached. They'll have reflectors. You get reflecting materials, it's already got a glue at the back, so you just applied them like a Scotch tape or something. Okay, the cooling machine, so that's what the manufacturer shows it, and that's what they look like in the catalog, which is what we purchased. The smallest one you can get commercially. And that's what they look like in real life, again, with my student. Here's what they look like, okay? They're nice looking machines. They're about a little more than a person's size, and remember, it's 40 degrees Fahrenheit in and 40 degrees Fahrenheit out. Okay. We intend to store cold water because the sun goes down around, 3 or 4 o'clock, and then we still want to be able to cool. So that's our cold water tank. And those are the only pieces I'll show you. Those are the impressive pieces of the machine, the collectors, and this is big too. Everything else is kind of normal looking. Okay, so I'm going to change to the other aspect of our work, which is photovoltaics. And I probably should pause here for a question or two.
Any questions?
So that application that you're building that prototype for is for
Cooling.
chilled water?
Chilled water.
Is there a certain application you have?
Well, we're
developing countries or?
our application is to cool and enclose. We're buying a big trailer and just cooling the trailer, just to show. We're a university group, right? We want to show what can be done.
Okay. Then are you going to apply the tracking technology at some point, or?
What we're using this technology, okay?
Right.
Yeah. Yeah. Yes.
Roughly what does the commercial chiller cost?
Okay. The big-sized ones are actually quite inexpensive. They're about $500 a refrigeration ton. The small ones are expensive. So the small one, in fact, you get a notion when it's called a villa model. So people who can afford this have villas, okay? But I would say on a 50-ton and up scale, it's about $500 a ton, which is quite comparable to compression machines, I think.
So how many refrigeration tons was that one?
6.5. Good, those are good questions. Are there more?
I think just to clarify from my understanding is that with your collector, you don't need tracking to get the same performance, right?
Of course not.
Yeah.
Get better performance.
Yeah.
We get the diffuse radiation.
So
I should
to
say.
answer that question, it's not
Yeah, we see the whole sky. Tracking collectors only see the sun, okay? Yeah.
With these collectors, do you have an estimate for dollars per watt?
We do. That's a good one, because we think we're at something between $100 to $200 per kilowatt, something like that. Yeah, Eli.
So this particular model that we're looking at, what is the acceptance angle?
The whole sky, the sky. I mean, 60 degrees, right? Plus
But
120.
My understanding is if there's some concentration, you've given up some
Yeah.
percentage of the
Well,
sky.
yeah. It's you've given up what's beyond 120. So it's very little. It's 1 over C, and C is like 1.2 or something. So you collect 1 over 1.2. But you do a bit better because the sky's a bit brighter where the sun is than it isn't there. So for all practical purposes, you see the sky. Okay, maybe I'll continue. Okay, photovoltaics. So, we started, it's hard to see. We started with the advent of the high efficiency multi-junction cell. Actually, what happened to me was shortly after I landed in Merced, 2 gentlemen from Silicon Valley came by in their own airplane. Now we have an advantage. We have an airport. Right? We can walk from the airport to my lab. Okay, and they showed me a little cell, 1 centimeter cell. They told me it was in the high 30s, and I was astonished. I said I'd never seen anything like it. And they said, but it needs high concentration because it's very, very expensive. Also, it works better under concentration. So, are you interested in working on this? I said, sure, this is great. So we started to work on this, and out of this came a successful Silicon Valley company. So we're very pleased with that result, okay? But first, you need to know a bit about these cells. So it's a busy graph. It's an NREL graph, and most of these technologies, I could spend time on them if you ask me questions about them, but the one we're talking about now is the multi-junction. It's the one, it's sort of like going from monochrome to color, okay? It's a 3-color cell, so you get the broad spectrum instead of a single color, narrow spectrum. So they push up to 40%. I think it's over 40% now. Over 40% in the lab. In the high 30s in the store, you buy them. They're expensive, okay? And yeah, here's the idea. So it's 3 layers, three different band gaps, so 3 colors, okay? So it's a very promising technology. I mean these are probably heading toward 50%. At that point, you're quite comparable to conventional power generation, and really you can imagine competing with utilities if you do it right. Okay, so if you look at the technology, it starts with huge concentration, huge concentrators which end up being now rather small, and from huge to, I'll be talking more about this and this. So we were very proud of this, okay? We ended up with a nice little compact thing here, and it became the basis of a company, okay? So it looks like. And so that's about 17 watts electric, that kind of thing. That's what they look like in modules. And yeah, I did list the company here. And then some of the work we do to try to make this flux more uniform, these are, I would say, in the way of details. But that's what we do, so we're quite proud of it, okay? So you can imagine them on rooftops. I think the current thinking is more utility scale. I'll show you a picture of a real life one in just a second. Here's a miniaturized version where the things are only millimeter cells and only an inch or so. So looks like that. millimeter cells. Okay. How they might look in a module. And here's a real thing. So this is at the Palo Alto Water District, and that gentleman is one of the two that flew into our lab a few years ago, and that's me. So that's what they look like. Of course, they have to track. They're high concentration. They have to track.
What's the output of that panel?
Yeah, well, you have to multiply 17 with the number. It's kilowatts, but I don't remember. I should know. I should know right off the top, but I don't. Okay. I think some of the nicest things we've done as a university group is to find other ways of concentrating, of high concentration, which has the benefits of thermodynamic efficiency and is also practical, okay? Now, Fresnel lenses are nice and practical. Why? Maybe I should make a comment. The best systems from both a practical point of view and a cost point of view, and probably just an intrinsic point of view, the less material the better, okay? If your system has no material at all, that's the very best, but you need something. So the less material, the better. So Fresnel lenses, as you probably know, are very thin material and very little material, very lightweight, very little material. Okay. However, they got problems. They have I almost used a bad word. They have poor thermodynamic efficiency. In other words, they don't have sine theta concentration. They have 1/10 of sine theta concentration. Okay. And they produce very ununiform flux on the cells. The cells don't work very well. The hotspot problem, and you need to do something. That something is what I've been telling you about. This string optics can actually boost the efficiency up to thermodynamic levels and can get rid of the hotspots. So you can go from hotspots to uniform. How do we do it? Very simple. Just have a thin Fresnel lens and a secondary string thing over here on top of a cell. This is very simple. So it's simple, yes, and we're just gradually seeing this kind of thing emerge in the real world. You see, mostly when you see Fresnel lenses, you see the ones that just have a Fresnel lens in a cell. And they're very poor thermodynamically, which means that they don't work very well. The tracking is not precise enough, etc. But by adding non-imaging optics, we can make them into practical systems, and we're just barely starting to see them emerge, okay? And I think we'll see more and more of these kind of things. I personally think this is probably one hesitates to ever predict things, but I think this is probably the best solution for high concentration PB, I think. Okay.
Can I ask, what is the balance between tracking versus non-tracking?
I mean,
How do you decide in a system like this?
this has to track. I should have, there's a table somewhere I glossed over. After about 4, so you have to start tracking. You have to start adjusting anyway, after about 4. So by the time you get to these are over 1,000, so you better be tracking pretty precisely. But about a degree or so, it's not worse than that. So you just think of the sine squared theta thing. Other questions? Okay. So we've done that. A bit about lighting. We've taken the same. Yeah, our guinea pig is the state's collection of minerals, which happens to be in Mariposa, which is a lovely town on the way to Yosemite, and it's a gorgeous collection. It includes the largest gold nugget ever found in the state. Okay, and we were asked to see if we could light the museum because they liked the idea of sunlight, daylight, instead of artificial lights for many reasons. And those are some of the reasons. Okay. They didn't like the heat. They didn't like the UV. And so we thought about using our techniques for daylighting. And of course, Skylights are well known. We want to do something that we thought was more practical than skylights because they really didn't want big holes in their roof. So here's their famous gold nugget. They have all kinds of lovely minerals in there. So what did we do? We took our photovoltaic system and replaced the cell by a flexible light pipe, not fiber optics. Fiber optics is not only not too efficient, but also very, very costly. No, these are large diameter, you can think of them as garden hoses, very large diameter, but they're flexible light pipes. And they're made commercially. You don't have to invent those. So this just shows people less sophisticated than this audience how these things work, okay? And I guess that's kind of an example of light coming out, okay? So by going 500x, we can put the light into a rather small opening. So we're actually on the way to demonstrating this in the museum, and that's due to happen this semester. It's a student project, okay? That is what the museum might look like if they could raise enough money. Right now, the museum is in a temporary building on the Mariposa Fairgrounds, and it's probably a better kind of building to be a guinea pig for what we're doing because we're putting holes in the wall, stuff like that, okay? Okay. So I'm about to leave daylighting. Is there anybody want to ask about that? I'll say one more thing. So we have a, I guess as any university, we have a social science management types curriculum, and the management students have gotten so interested in this that we actually have a group of them who are looking at this as a new kind of venture. So I fully expect this to be a startup out of UC Merced. I think it's very likely. Okay. All right. Back to thermodynamics, okay? Back to saying, how does thermodynamics understand the second? How does geometrical optics understand the second law? How does that happen? And I'm calling this part beating Liouville theorem, okay? Liouville theorem tells you that it's 1 over sine squared theta, best you can do. You can actually do better, as Professor Jablonovich has pointed out in some beautiful papers. So I want to tell you about that because it is also the basis of a research project right now, so I think kind of interesting. All right. So first of all, if you look at a really good text in statistical physics, it's got two good things about it. First of all, it's, and Eli sent me onto it. First of all, it's written by 2 brilliant physicists, right, Landau Lishitz, but it's also translated by 2 brilliant physicists, Sir Rudolf Parles and his wife. So you got a double thing going for you. Unfortunately lost because future editions of this got translated by somebody else and totally got ruined. But anyhow, if you go back to the original one. On page 1, the book tells us that to formulate the basic problem of classical statistics, you have to introduce phase space. Page 1, okay? And what's phase space? Delta P, delta Q, which we'll be continually using later on. Page 24, just a few pages later, the entropy is just the log of the phase space. Page 24, okay? So, what's that got to do with optics? Simple. This fancy A10 concept, that's just phase space, okay, essentially. I mean, if you're technical, it's the 4-dimensional. Never mind, it's phase space. What's brightness? Brightness is power divided by A10 power divided by phase space. Therefore, the entropy is logarithmic with the A10 so it's logarithmic with the brightness, okay? So the entropy is logarithmic with brightness. What does that mean? It means that the brightness is exponential with the entropy. And everybody knows that when you change entropy, the change is linear with the heat, right? Everybody knows that change in entropy is associated with heat divided by temperature. So we'll use that to beat the Liouville theorem, beat the brightness theorem, and get potentially a huge gain in brightness, which is to say a huge gain in concentration. Okay, so there's a little group going on in Chicago with Cy Gosh, Dave Pelka, students, one of whom is here. Chunma, raise your hand. Right here. And Sue Carter's group at UCSC, okay? We're trying to make these things and try them out. So the idea here is to get some change in entropy, to put some heat into the environment by downshifting, by changing the solar spectrum a little bit, just a little bit will do, a little bit of a shift will do. So the idea is to have just a plain device here and get concentrated light off the ends. So here's a little bit, go back to thermodynamics. I told you that the brightness is just the power divided by the phase space, okay? I told you that the entropy is logarithmic with the phase space, and therefore the brightness can be exponential with the change in entropy. And everybody knows that the change in entropy is delta Q over T. So if the light deposits a little bit of heat to this material, then the amount, the exponential has a heat deposited, which is just h nu minus h nu prime over kT. Again, kT is room temperature, so this is huge. Even a fraction of an electron volt, this is enormous. Will we ever get it? Probably not. And there's a factor here which, if you look at it in more detail and study Professor Yablanovich's work, you'll get that factor too. It has to do with the fact that A10 was 4-dimensional, the phase space is 3-dimensional. It's 6-dimensional. Anyway, mainly it's the exponential factor which gets you this increase. Okay. So can this work? Well, we're trying. Okay. So we put material in here which can downshift, and then we measure the light coming at the edge. If it did work, it'd be very, very nice. Why? No tracking, no optics. Okay, so it's so you take all the light, whether it's diffuse or direct, and lots of other nice things about it. So basically, this would be a nice way of making windows if you could do it. Okay, so compare this kind of thing, which just slabs of material, which nothing has to move with the tracking concentrator. So if both of these could concentrate, this would be interesting. Well, we're trying. Lots of groups are trying. Okay. So I want to do one more thing before I quit. Maybe two more things. How much time do I have?
About 5 minutes.
One more thing. I want to show you there's intellectual content to what we do. So I want to show you that it's not all just, well, I shouldn't say just, it's not all experiments, okay? So we had an interesting idea, I think interesting enough to tell you a bit about it, okay? It's very recent. It came out this month in Optics Letters. Okay, so what I wanted you to see here is just the first sentence. I'll read it to you. Perfect imaging has been a desired goal of optics from the days of Galileo, Newton, and Descartes. So I got away with that statement. If you think about it, send this to a journal, you expect a lot of flack. Instead, we got congratulations from the reviewers, okay? So this is out this month. And it's so neat, I want to show it to you. By the way, here are the people who worked on this problem. I'll put this on for a few minutes, for a minute. So it has a very distinguished history, okay? Okay. Well, here's how it works. So I'll quickly run through for you what we tried to do. It's a fancy word for perfect imaging, eggplant has. It's just a fancy word for perfect imaging, okay? And you satisfy the Abbe-Sine condition, which is a very peculiar condition. This one you probably learned in school. It's a condition which, on axis, guarantees you good off-axis performance, good imaging performance. It's very peculiar. This is why it's fascinating all those people. It's very, very peculiar condition. So the condition is that a parallel beam, completely parallel beam, light from a star, okay? When it's converging on a focus, will intercept the convergent rays on a sphere, okay? Very peculiar condition, which guarantees the sign condition. Very, very strange, almost mysterious. Okay. So, how do you do it? Well, two conditions. You need two surfaces. You need, you've got imaging, you have the AME. You need two surfaces. And the two mirror solution is well worked out in a beautiful book by Lundberg from the Berkeley Press, okay, quite some years ago. Analytical solutions by, this is the famous Schwarzschild, the one who thought up the Schwarzschild metric. And so this is a famous problem, okay? And Lyndon Bell is a mathematician who wrote in recently in the astronomical, the Royal Society of, it's one of these obscure Royal Society journals, which I can't remember the name. Okay, so here's the Lundberg method, how you solve the problem. Okay? We're going to have two surfaces, and we'll quickly go through it, and we'll adjust those surfaces to make sure the intersections are always on the sphere. And thereby develop two surfaces. Okay? Problem. What's the problem? You probably already saw the problem. These are two mirror surfaces. The problem is that the front surface, if you fully develop it, it blocks the light. So you've got a beautiful mathematical solution. Can't use it because this front surface blocks light. So what people do in practice, they leave most of the surface out and just use a small bit in the center, and thereby the blockage is not too bad, but you don't get the full benefit. So we asked ourselves, can we get the full benefit by having a one-way mirror? Plus, a one-way mirror can be achieved by internal reflection, right? So, total internal reflection is a one-way mirror, if the angles are right. You have to go beyond the critical angle, okay? So, here's how we solve the problem. Now, if you follow Lundberg, you find you can't do it. Because the ray in the next step is disturbed by the refractive surface, which you don't know yet. There's a causality problem, so you're stuck. We thought it was impossible. You're stuck, okay? And we solved it thanks to a brilliant postdoc I have right now, Leia Zhang. We solved it by finding an initial configuration where we knew the answer. An initial configuration where the ray is sent back to itself. We knew the answer, okay? And therefore you can, now causality doesn't, now you're going backwards. Causality is okay if you think backwards. We know our history very well, we just don't know our future, right? So now you need to know your history that you do know very well, and you solve the problem, like so. And that's what they look like. So, will these be useful? I think so. Will we see them? I hope so. But that's what they look like. Look like nice saucers. Do they work? Yes. Look at the off-axis performance of a parabola where focused light gets totally spread out to this sort of design where the focused light gets nicely contained. So they do work. Okay. I think I'm on time. I was going to show you one more thing, but maybe I'll wait if there's a question or two. Maybe I'll do one more thing.
Okay, thank you.